Good afternoon. It's the beginning of the semester. Usually the sound I get at the end of the semester. Okay, let's try again. Get some air in your lungs. We need a lot of air and oxygen today in our experiments. Good afternoon.
Good afternoon.
Thank you very much. That's more lively. Welcome to Chem 1A. That's it. Woo. The one and only, Chem 1A. My name is Heino Nitsche, N-I-T-S-C-H-E, Nitsche. I will have the honor to be your professor for this semester for Chem 1A. Most important for you, B-space. There is the URL for B-space. Who has never been at B-space? Excellent, I don't have to say anything. You go to Chem 1A. Before you write any email or send out any requests or something, go to B-space and read about it. The likelihood that your question will be answered is very high if you go to B-space, about scores, about the labs, and all kinds of things. And then your lab instructor and lecturer is she's right here, Dr. Lee, Dr. Chunmei Lee. She is in charge for everything concerning the lab, all the GSIs, the TAs. That's her métier, okay? Then we have, next to Dr. Lee, we have Dr. Lamoureux. He is in charge for a very, very sensitive issue, that's enrollment, and the managing of the logistics of this whole Chem 1A setup. So we are very grateful for him that he does this. And I think he has done such a tremendous job to get you into that class here that he deserves a hand. He doesn't like it, that's why I do it. Okay. And next to him, not next to him, I'm not pointing with the laser pointer at you. This is a little bit in the dark here, is Ms. Karen Chang. She's the demo supervisor. She will take care of all the demos for me and whoever else is lecturing. And this is a big job, and I'm very grateful that she does that. And then we have Mr. Hickory here, number 15. This is Greg Dellinger. He is the head TA, and he will hold some lectures for you, and he will also hold some review sessions for you, and I'll talk about this in a little while. If you have any questions concerning Chem 1A, after you perused B-space, then you can write to chem1a.sp10@gmail.com, and he will try to answer you as fast as he can. There will be lots of questions at the beginning, but let's see. Don't overwhelm him, please. Office hours. I have office hours Wednesdays from 4 to 5 and Fridays from 3 to 4. This is PM. The location is 446 Latimer. That's my office. It's out the hallway. This building is called Latimer. The next building over. The next building, not over. It's called Latimer. You go to the 4th floor, go out of the elevator to the left, and you will come by my office. I'm starting office hours today. So if you have any questions, come and see me. Don't come 5 minutes before the midterm or final. Oh, I have these questions and so on, okay? I won't be able to do it because there will be another 200 people in front of my door, all right? Just come in, it's an open office hour, just come in and enjoy the ride. We have weekly review sessions. Greg will give these sessions. They are Thursdays, starting this Thursday, i.e. tomorrow, from 5 to 7 p.m. at 1 Pimentel Hall. This is 1 Pimentel Hall, that's where you are. So it's going to be from 5 to 7, and tomorrow he will talk about OWL and about the things that we have discussed this week, or that we are going to discuss this week. So this is a free format. Use the opportunity to ask questions and get them answered by our head TA, Greg Dellinger. We also have open office for you, open office hours, so you can drop in with any question that you have, and this will be staffed usually from 10 to 3 by a GSI or a TA, and the office is B12 Latimer. It's just around the corner. So essentially, if you go around the corner, the first office to the right is the open office. You can come there. We start next week. You can come there and ask questions. Okay, we try to offer you as many possibilities to review and to help you with the subject matter. I also would like to mention that there is the Student Learning Center. They also teach Chem 1A, or they help you with Chem 1A. They have GSIs there. And don't be shy of going there. It's, I don't need to, I'm too good, I don't need to. There's only the bad guys go there, okay? So that's the wrong attitude. Get all the help that you can get, right? That's the most important thing. You want to ace this thing here. And it's not going to be easy, but I will try to help you wherever I can. You're at Berkeley here, okay? How many of you were valedictorian in that class? Not that many. What happened to Berkeley? Okay, usually 60% raise their hands, and then they say, oh, this person must be at least as good as I am, okay? So you are all very good, otherwise you wouldn't be here in Berkeley. Okay? So I'm trying to teach up a little bit. And this is my first question, my first Chem quiz question. So who has no iClicker yet? All right. Not good, but doable. Because we are going to count the iClickers from Monday on, and this works as follows. I will ask you some questions, will be more difficult than these questions, during the lecture, related to the subject that I just taught you, and then you will think about this on your own and give me an answer within 2 minutes, A, B, or C. And then I see how well you have taken up the material that I have presented to you, and I tried to think of another way to explaining it to you if it wasn't too successful. And I give you some more pointers and hints, and then I ask you to acquaint yourself with the person behind, in the front, on the side, and chat about the subject, okay? So you have a discussion about the subject, and then after 2 minutes, you give me either the same answer or a revised answer. And then we will look at the score, and I will see if this has improved it, or if this is such a problem that nobody gets it, or very few people get it, okay? And then I will explain it to you again and give you the solutions. You will get attendance points for this. Attendance points will be 50 extra points on top of the 1,000 that you get to it for an A. We have the scale, the grading scale is on the webpage on BSpace. We don't grade on a scale. We have solid grading intervals, okay? So you get 50 extra points that will help, and you don't have to be there. But you have to use your own iClicker. You cannot use anybody else's iClicker or click in for somebody else. They said, oh, I don't feel like it to go there today. Five guys or 5 people give you the iClicker and you click. You're in deep doo-doo if you get caught, okay? Because you ever heard of the student conduct, the rule of student conduct? Okay, I think that's been handed to you when you started. Let's talk about the positive things. So there's going to be a whole lot of fun, this whole thing, okay? So the question is now that I pose to you, how many years of chemistry did you have in high school? I don't think you need two minutes for that, to do that. And you click A, absolutely, B, undecided, C, no. What happened? Oh, we have the second question. That's not good. Let's stop this again. Why don't we try that one? Let's do that question. Do you plan to go to medical school? Absolutely, undecided, or no? So that's a longer thought process, but I'm not going to give you 2 minutes for this, okay? I just want to see how many people have iClickers. And this is all practice. Make sure that you have fresh batteries in your iClicker. You can't come afterwards and say, oh, Professor, my batteries ran out. I say, I understand, and I would like to help you, but I can't, because if I help you, then I have to help all the other 200, all right? And so that will be an absolute nightmare to record this in iClicker. So let's stop it. 106 have iClickers. So let's display it. There's about 40% want to go to medical school. What happened? That's okay. You know how much tuition is? $9,000 or something, isn't it? Does your parents pay that? I think they wouldn't be and this is funny one time, but it's going to happen a lot of times, okay? It's not funny, actually, because you're paying a lot of money to sit here. And so you really need to use your time to work off that money, because your parents, they're really scrapping it together in order to get you here. Some of you at least, okay? So I expect you to be not sincere. That's a fine thing, you know, but it will not happen too often, I think. All right, so we have that question answered, and then we're going to go back. How did that happen? Did I click too often, or what did I do? I'm going in the wrong direction. Did I delete it? There it is. Okay. Direction is very important. How many years of chemistry did you have in high school? You always wanted to do that. That's John Schenker up there. Okay, that's not a difficult question. We are done already. Wow. I don't know what's going on here. Excellent, excellent. You know all the stuff I'm going to teach you, but don't get in a trap. Don't fall in a trap. Just make sure that you are on the ball with this, because you had more than 1 year of chemistry in high school. Many of you had AP. This is D's AP, yeah? I assume it's AP, okay? Good. So let's go on with this here. So you've seen how iClicker works or not work? So in the lab, some of you have started already. You design a reaction using acetic acid and sodium bicarbonate that it will evolve the largest amount of CO2 gas to inflate a plastic bag, okay? So that's an air bag, not the one I would like to have in my car though. But in order to do this, you need tools such as stoichiometry, what we talk about here today, molar mass, balancing chemical equations, to predict what will optimize your airbag. You want to have the biggest airbag there is, okay? So you've got to calculate this well and then make that experiment. Let's do it. Chemistry. Chemistry is everywhere. As I speak to you, my body processes or does many, many chemical reactions to make me walk, to make me speak, and for you to listen, you're processing constantly chemical reactions for that to do. So chemistry is omnipresent, it's everywhere, and this is why we are here. We need to learn about this. And there are two kinds of chemistry. The one where we can look at elements, that's the science of elements. So this is carbon. Okay. This is carbon. All right. This is not too interesting, isn't it? We know much about carbon. But what really is interesting is the reaction of elements and molecules with each other. Okay? And they have an energy state at the beginning, they call it the reactants, and then they react with each other. Either they give off energy, then they are in a lower energy state, or we need to put in energy to make this reaction happen, then they are in a higher energy state. All right? So if you look at the energy state at the beginning and at the end, some chemistry has happened, and this is chemistry. So we can describe chemistry by the difference in energy states. This is called thermodynamics. How we got there has nothing to do with the chemistry. It has to do with the chemistry, but not the chemistry we are interested in. That's called kinetics, how you get there. We are dealing this semester with thermodynamics exclusively, of course some other things, but we are not dealing with kinetics. So let's have a look at a chemical reaction. So we have hydrogen and oxygen to form water. Hydrogen and oxygen to form water. Okay? Now, let's do that. I have a balloon with hydrogen here. I have to put it in a balloon, otherwise it would immediately disappear. And so now I want to let it react with oxygen. But there's no oxygen in the balloon. How can I make it react with oxygen? Pop it? Would that do it? So if I pop it, it wouldn't do it. I tell you, I don't have an extra balloon, otherwise I would do it, okay? That's a good idea, pop it. And if I pop it, Nothing will happen. The hydrogen gas will go away. Go ahead. You don't have to. Just shout it out. I burn it. And by burning it, what happens then? Where does the oxygen come from? Where does the oxygen? Take a deep breath. Where does the oxygen come from? From this room here. How much oxygen is in this room? How much? 20%. What else is it we are breathing here? Carbon dioxide. Very small amount, but very important issue. When I was your age, the carbon dioxide level in air was 350 parts per million. It's now 370 parts per million. This is that's one of the causes of global warming. Carbon dioxide is not a major component, though, but an important component. What else? Nitrogen. How much about? 70%. Okay, and a little argon and that stuff in there. So what I will do is I will pop that balloon, and there will be two things happening. First, the balloon will crack, and then you will hear something. There we go. That was pretty good. Wow! So each molecule of hydrogen has to find a molecule of oxygen. Actually, you need two molecules of hydrogen to find one molecule of oxygen. So this is out there in the air. And it takes a little while for that hydrogen to find that oxygen and to react. Okay? So this was a pretty powerful explosion, but it was a little bit drawn out. It lasted for maybe a second, isn't it? Or half a second. So there was a relatively big fireball with that. So we have these two elements or atoms, molecules in an initial state, and this is in the final state, and the difference we released it as energy. Okay? The difference we released as energy. So this was what happened. This is our hydrogen, obviously, and this is our oxygen. Now what's the next possibility? What can we do to accelerate this a little bit? No, the heat is not it. I explained to you why the heat has to be there in a little while. So, how can you get that closer to the hydrogen, the oxygen? Put it in the balloon. Exactly. So this is what we've seen. The reactants, these are those guys, and the products, this is the energy scale. It was higher here and lower here. Okay? And the difference you've seen in the Big Bang and going out as energy. So what you also see is that we have to overcome this energy barrier. Okay, this is sort of a high road that we have to overcome. This is a transition state. So what has to happen is to overcome this barrier, we put this flame on there. And a few of the molecules will get this high enough energy to overcome that barrier, will make the product, and then release more energy, which will help the other molecules to overcome that barrier and to make that reaction. So this is an activation barrier. That's why we need a little bit of flame. I don't have a smaller flame, but even a small flame would do it, a very small flame. So even the light switch sometimes, if you have that's how explosions happen, the gas explosion, for example, you have a room filled of gas, somebody flips the light switch, everybody's gone. Okay, and this was just one little spark. Okay, this provided the energy for the first couple of molecules to get over the hump, and then the rest of the energy is released by that reaction to get the rest over that hump, over that energy hump. Okay? But we are actually not interested that much in this. We are interested in the reactants and the products. And now the suggestion was we put it in the balloon directly. So I think you need to cover your ears now. I better get my glasses. So that should be a more vivid reaction. Holy cow! My God! So what I said was right. We had it right there, and it was not so drawn out. It was much louder, much faster. So because the molecules were right there, but we can make it even better, hopefully. So we had a ratio there of oxygen and hydrogen. And we had 1 part oxygen and 1 part hydrogen. How could we improve that reaction to make it even go better? Look at that equation. You need 2 volumes of hydrogen and 1 volume of oxygen to make 2 volumes of water. So this is the stoichiometric factor. This is stoichiometry. The right ratio to complete the reaction to the final point. If you have too much hydrogen in there, it will use up the oxygen and some hydrogen will be left over. If you have too much oxygen, it will use up the hydrogen and oxygen will be left over. Okay? So you have to have the right ratio, the right stoichiometry according to this equation in order to make the optimal reaction. Let's do that, huh? Let's see if what my animation says here. Yeah, we put it inside, we did that, and I hope. So, I need to put this over here. Think it's going to be louder? Going to blow John Schenker out of his booth up there?
I don't think so.
Okay. Cover your ears. By the way, there was in 4B they did a similar thing. Somebody's contact lenses dropped out of his eye. You know? But it's not going to happen here. It's not that powerful. Okay? All righty. Are you ready? Yeah. Did you see the difference? Holy, wow, 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 wow. I scared myself. So now we have it in the right ratio. 2 volumes of hydrogen and 1 volume of oxygen. This is what Karen put in there. And with this, we have it in a stoichiometric ratio. That is what stoichiometry is all about. So the question is now, it's easy to do it with gases. Because this guy Avogadro said, equal volumes of gases, or gases that have the same volume, have the same number of molecules or particles. Okay? So if you take hydrogen, you take so what do we want? We want 2 parts of, let me go back, we want 2 parts of hydrogen and 1 part of oxygen. So she fills the balloon 2/3 with hydrogen, 1/3 with oxygen, and we are ready. The other one was half-half, and the other one had the oxygen outside. All right? So this is easy with gases. It's very easy with gases because of this Avogadro's discovery. But if you have solids or solutions, it's much more difficult to do. How do I know what is the right ratio? So, and as you see, this happened on an atomistic basis. Each atom has to find the other atom, or each molecule has to find the other molecule to react. And all of them do this, all at the same time or after one another, but very quickly. And so if I have a solid, how would I now get the right amount? So I would have to weigh it. I would have to weigh it, and I would have to know if I weigh something A and weigh something B, how many atoms are in A and how many atoms are in B. This is how it works. And so nowadays we can see atoms actually. We have these, in the old days we used to have optical microscope. I think when some of you were kids, they probably had an optical microscope, probably on the computer even. And so you could take out a hair and look at the hair. Oh, that's so big, okay? But it's very, very, very big compared to an atom. So this is microscopic view, and then you have the macroscopic view, not the microscopic, the nanoscopic view. This is on a nanoscale. So atoms are many nanoparticles. It's on a nanoscale, 1,000 times smaller than the microscale. And so we can, here for example, there's some scanning electron or scanning tunneling microscope, and the point is that you have a different wavelengths that you scatter off these objects. If you look at your microscope, anything scatters in the visible. And the visible light has a different wavelengths than the electrons will have, and I will explain to you this to you in another lecture. So the scanning tunneling microscope, for example, you have these are nickel atoms, and they are placed on this is a copper surface, and they move these nickel atoms around on that surface. It's just amazing. You can see single atoms. Yeah? Here you have cobalt, a ring of cobalt atoms placed on a copper. That's the copper surface, and that's the ring of cobalt atom. That's a cobalt atom. Looks funny, doesn't it? And so this is absolutely the new thing, nanoscience. We do everything on a much smaller scale now because we know how to see it. We do understand the reactions. And so you got much more reactivity, for example, because you have much more surface if you have a bulk of this. Okay, nanoscience. So the question is, how do we do solids? How do we get this macroscopic, the bulk? We have a pound of something, and we want to react it with 5 pounds of something else. How do we get this in the right ratio? So we need to go, the macroscopic, we need to adjust it that it has the right microscopic, or nanoscopic is much better ratio. Microscopic is not small enough. It has to be on the nanoscale that we do atom by atom or molecule by molecule. So what we have here is Avogadro's number. This is a unit, a chemical unit, and is 6.022 times 10 to the 23rd. Anything. It's just 6.022 times 10 to the 23rd. You know, when you go to the shoe store and say, I would like to buy a pair of shoes, and the guy doesn't give you 3, he gives you 2, okay? Or the clerk gives you 2. So a pair of shoes is a secret code. A pair of shoes, okay? That's 2. How about a dozen? I don't know what dozen or 12, what's easier to say, but a dozen stands for 12, okay? 12 anything. 12 hands, a dozen hands. A baker's dozen, another secret code. Very secret. Baker's dozen. What's a baker's dozen? 13. See, everybody knows that code. Now we have our own secret code in chemistry. Avogadro's number, 6.022 times 10 to the 23rd. You can have 6.022 times 10 to the 23rd shoes. It would be still Avogadro's number of shoes. Okay? Or eggs, or anything you want. But that's not very practical, because if we take, for example, marshmallows, and we take a number, Avogadro's number of marshmallows, 6.022 times 10 to the 23rd. It's such a huge number of anything. It's more stars, larger than the number of stars in our universe. Okay? And if we come back to the marshmallow example, if you cover the surface of the earth with marshmallows, you would get a coverage up to 600 miles all around the earth. That's so much. That's a number, it's a billion, million. It's huge, absolutely huge. So if you, for example, you would have 6.022 times 10 to the 23 pennies. Okay? This is 6.022 times 10 to the $21. That's a lot of money, isn't it? Okay. Now, we decide we're going to give everyone in the United States a fair share, an equal share of this. That equal share is, we are about 300 million now, 304 million, okay? So we have 6.66 times 10 to the 21, that's the dollars, divided by, what was it, 3 times 10 to the 300, 3 times 10 to the 8, okay? 3 times 10 to the 8, this gives 2 times 10 to the 13 dollars per person. 2 times 10 to the 13 dollars per person, so that would be 20 trillion per person. Now our national debt is, as of today, 12.4 trillion. But each citizen, we have just given each citizen 20 trillion. So you just single-handedly pay off the national debt with that. And you still have, you have 1.6 times more than the national debt, okay? So you have 60% left. That's pretty good. Can you give me some of that? Okay, it shows you how big that number is. It's huge. But fortunately, atoms are very small, extremely small. And if you have a mole of atoms, that's the number you can handle, but the amount you can handle, okay? A mole of atoms, a mole of elements, and this is we call this a mole. 6.022 times 10 to the 23rd is a mole for a chemist. And we always mean a mole of something, a mole of atoms. We don't mean a mole of shoes, okay? But you could use it, like the baker's dozen. And so now what we do, we have to set a standard. We need to find some kind of a compound which we know has exactly 1 mole, and then we weigh that compound. Then we know 1 mole of that compound has that mass. All right? So, and that compound is carbon 12. Carbon is a natural element. In nature, it comes as carbon isotope 12, carbon isotope 13, and carbon isotope 14. But when the standard was set, the standard is carbon 12 isotope. It's not natural carbon, okay? So, and you have exactly in 12 grams of carbon 12, you have exactly 1 mole of carbon atoms, all right? So now it's easy. Now we just measure everything relative to that standard. So if it's 15 times heavier than that, then it's a much heavier element, and we know I need 15 grams instead of 1 gram to get the same amount of moles, okay, or a fraction of moles. That's what it is all about. So, and your molar mass is given in your periodic table, in your periodic tables, and you see carbon 12 is not in there because it's a periodic table, it's not an isotope table. Carbon 12, some of you can read this, I read it for you. The molar mass is 12.011 grams per mole. Grams per mole. That's the molar mass. All right? That's fantastic. Yeah. And so it's 12.01. So why is it? Because it's the average of the isotopes. And the abundance of carbon 12, carbon 13, and carbon 14 is much smaller than the abundance of carbon 12. So this is why this is a fractional number. And this is why you have oxygen, for example, oxygen 16 and oxygen 18 or oxygen 15. You have 15.9994. So there's oxygen 15 in there, okay? That's why it's lower. A little bit lower, not much. So we have if you want to know the mass of 1 atom, the mass of 1 atom, it would be incredibly small in mass. So carbon 12 is assigned exactly 12 atomic mass units, okay? What does that mean? It means that carbon 12 is assigned 12 atomic mass units, okay? And if you have, just make sure I have the right thing here. So 1 atomic mass unit is then 1/12 of the mass of a single carbon 12 atom. That's a very small number. So 1 single atom then weighs 12 atomic mass units. Of carbon. 1 single atom of oxygen would weigh 15.999 atomic mass units. All right? So we just make this atomic mass unit because we don't want to say this small number of the minus 27 kilograms. And so I already said that the masses of all other atoms are given relative to the standard of carbon 12. All right? And the atomic masses are averages of isotopic masses. That's why they are fractional numbers in the mass table. Okay? And now there's a relationship between atomic mass units and grams. And the relationship is 1 atomic mass unit is 1.66 times 10 to the minus 24 grams, or 1.66 times 10 to the minus 24 grams, or even 1.66 times 10 minus 27 kilograms. And we don't want to use this, especially in physics, you don't want to use that. That's why you have the atomic mass unit, and you say 1A or 1U or 1 AMU, and this means that here, okay? So 6.02 times 10 to the 23rd atomic mass units is then 1 gram. This is what we just did. And this we did already. If you have, this is the mass of one atom, and you multiply this 1 mole, then you have the 12 grams. So we did the definition backwards and forwards. Okay. Good. So the atomic masses and molecular masses, the atomic masses don't add up. They are averages of the isotopic masses, but the molecular masses add up. So your hydrogen has atomic mass of 1.01 grams per mole. Hydrogen molecule has 2.02 grams per mole. I have 2 of those. Carbon-12, we have defined that, not we, the IUPAC, is 12 grams per mole, but carbon, the carbon that we deal with every day, is 12.01 grams per mole. Oxygen has 16 grams per mole. Aluminum, 27, 26.98. So if you have hydrogen, you need 2 hydrogen for water, it's 2.02, plus oxygen is 16. So hydrogen plus 2 hydrogen plus oxygen is H2O, is 18.02 grams. Carbon is 12.01, and 2 oxygens is 32, so you have 44.01 grams per mole for a CO2 molecule. That's the molecular mass, all right? So let's have a look at this quickly here. If I could have the camera and the light, and I need somebody who had a good lunch. Good lunch? Go ahead. So, if you could wear these gloves, please. They're fresh. You only use them 5 times. You're a bio major? See? I'm already training him. So we have 55 moles of different substances. 55 moles of carbon. Pretty easy, isn't it? 55 moles of aluminum. Is that heavier or lighter?
A little heavier.
Heavier, okay. 55 moles of lead. That's why I ask, no, not one hand. 55 moles of lead, okay?
Much heavier.
Much heavier, okay. About 55 moles of water. What do you think that volume is? 1 liter. It's about 55 moles of water. Okay? All right, what's your name again?
Parsa.
Parsa, that's your first name? Yep. Parsa, nice to meet you, Parsa. Give him a hand. The gloves are a souvenir. Okay? Go ahead, thank you, Parsa. So, and as I said earlier, this is why we could use these balloons so nicely. 22.4 liters is 1 mole of any gas. Ideal gas, of course, but we talk about the real gases later. There's not a big difference, okay? This is about the size of these balloons. Yeah? We popped up a mole of gases 3 times, okay? We are still alive. Now, let me ask you a question. We have methane here, and we reacted with oxygen. And this is a stoichiometrically balanced equation. So there is methane and oxygen, and methane, this is combustion. It forms, unfortunately, carbon dioxide. That's our problem. It will release energy, otherwise we wouldn't be doing this, and it creates water and carbon dioxide. So I have 4 grams of oxygen, 4 grams of oxygen, and I would like to know from you what mass in grams of methane do I need to react completely with this 4 grams of oxygen. I also give you that number, that oxygen, the oxygen molecule, O2, is about twice as heavy than the methane molecule. Okay? Now, why don't you think about this and use your eye clicker and give me your answer without discussing it with anybody except yourself. Is it 1 gram, 2 grams, or 4 grams? That's stoichiometry. You all had chemistry. Should all know that. But that's why you're here. So there is no grading on these questions, okay? But it would be advantageous for you if you get it right, at least the second time around. And it would also help me to see where you are. Starting Monday, it counts attendance points. But you don't have to come the whole thing. This lecture is podcast and webcast, so you can watch it over and over and over again, okay? And you can repeat my errors that I made over and over and over again. How many did we have initially on that number here, the second number? 140? 106. Wow. Okay, we do a hand thing then. Showing of hands, that I mean. Four have left the building. Okay. All right, they said, oh, the heck with this. Okay. Don't blame them. So, who doesn't have an eye clicker and means it's A? B? And C? Okay. All right. One of them is right. Let's have a look at this. Oh, not such a bad class. Pretty good, actually, for the first try. So why don't you discuss, so now you don't know which direction to go. So guessing doesn't help. You need to really know. So why don't you discuss this, introduce yourself to your person in front, in the back, on the sides, and discuss this with each other. Convince that person that your answer is right, and tell that person why the answer is right. Okay, and then vote again. Click in, come on, click in. Click in. That happens all the time that people forget to click in because they are so involved in the discussion. But I will give you a warning the last 10 seconds.
Professor Nitsche, please turn your microphone on.
Yes, Mr. Schenker, thank you very much. So don't forget to click in. Now you can click in still. Come on, go, 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 go. All right, because it will count that you were here. If you don't click in, I don't know that you were here. That's not too encouraging. So I must assume that most of them were guesses. One went this direction, one the other direction. So what we were, 38 before or something, isn't it? Yeah, something like that. Let me see what the previous one was. 37, 41. And this is 45, 51. Yeah, we got a little better in the wrong direction. In the wrong direction. Sorry. So, but you will understand in a second here. So we have, what was the question? The question was, what mass of methane is required to react completely with 4 grams of oxygen? We have 4 grams of oxygen. We wanted to react with methane. We know that oxygen is twice as heavy than methane, or methane is half the mass. So 4 grams of oxygen have a fixed number of molecules, right? Okay. So now 2 grams of methane have the same number of molecules because it's twice as heavy. Okay? Did you get that? But now comes the kicker. So you have 4 grams of oxygen. This is 2 moles here, okay? Or the stoichiometric ratio is 2 here. So now what do you have to do with the methane? You need only half the amount of methane. Because this is twice here. This is the oxygen, is your 4 grams. Okay, 2 grams would be 1-to-1 ratio. But you don't want a 1-to-1 ratio. You want a 1-to-2 ratio, so you need to take half of it. All right? Get it? Got to practice. There are going to be some homework things. The homework will be posted by tomorrow, and we give you till Wednesday. Usually the homework is due Monday morning, 9 o'clock. But there's some problem with the OWL system, and you have some problems, and so we give you some extra time. Okay? But this will be stuff of the homework. So we have seen hydrogen and oxygen forms water. Somebody asked me in the last lecture, where did the water go? It evaporated. There's a lot of water today in the air. High moisture content of the air. So we have 2 molecules here and 1 molecule here, but you don't make 3 molecules, you make 2 molecules. So molecules in chemical reactions are not conserved, okay? If you have 2 moles of this and 1 mole of this, you get 2 moles of water, all right? It's not 3 moles, not conserved. But if you have 16 grams or 2 grams of hydrogen, which is 16 and 16 grams of oxygen, you get 18 grams of water. Mass is always conserved. That's the important part. Don't get fooled. Mass is always conserved. So, in summary, what we have seen is that we have energetic reactions. We have reactants, that was the hydrogen and the oxygen, and we get them over that activation barrier by giving it a little kick, a little bit of energy. Not the whole reaction energy, just a little bit of energy. And we get them to the products. And these products are in a lower energy state. And the difference between this state, that difference here, that difference in energy, you've seen released. It was released, okay? This is called an exothermic reaction. Heat was released. There's the other possibility that you have an endothermic reaction, that the products are going up to here. They are higher. So you would have to put energy in there to get it up there. So the reactants, the products have a higher energy state than the reactants. That would be an endothermic reaction. Endothermic. So you have to put in energy in order for this to go. Don't mix this up with this activation energy. And the next time we make a little experiment, how to lower that activation energy, because that's what in industry happens. You don't want to have to put in a lot of energy in order to make a reaction happen. So you use a catalyst. And the catalyst will lower that barrier and will help with the reaction that you don't need to put hardly at all any energy in to do that. So I will see you on Friday.